Welcome to another unit in this methodology toolbox. This time I'm going to talk about clustering methods. With clustering approaches, we can differentiate very broadly between two approaches, meaning we have partitioning cluster analysis approaches and hierarchical. What's the real difference between these two? Well, with partitioning analysis or approaches, we assume our data set and we already know beforehand how many partitions, how many clusters we actually want to build. What the algorithm then does is find step after step what is the best segmentation, the best partitioning to put them into different groups. So here in this case, I told him I want to have 3 clusters, and he found the best partitioning of the whole space into 3 distinct groups, 3 distinct clusters. With hierarchical cluster analysis, I start with the same data set and then I summarize them step by step by step. First, I take a look which 2 are the closest together. That would be, for example, here Nike and Adidas. So I summarize them into one group. In the second step, the next 2 closest together would be Fila and Puma. So I summarize them into a group. At this point, I have 3 distinct clusters: the Reebok cluster, those 2, and these 2. If I want to stop, I can stop now. I could have stopped earlier as well, but I could also continue and say, well, they are still, my perception, close enough together, so I can summarize this cluster and that cluster into a larger one, giving me 2 clusters, the one on the left, the one on the right. Then in a final step, I could summarize all of them into a single group. And that's the actual interesting thing about hierarchical clusters. Here, we are not fixed to a certain given amount of partitions, of clusters, which needs to be known a priori. Here I can simply start with my data set. Then, when I feel, okay, of course I also have some algorithms with some underlying rules which say, well, this is enough clustering, here we stop. But basically at this situation I can decide when are the clusters too dissimilar to summarize them anymore. So here I'm working more or less from an exploratory point of view. Here I'm just already establishing a structure which was given from the outset. With those starting comments, we can go even further, in particular if you take a look at hierarchical clustering. Here we can first off differentiate how do we measure and how do we interpret differences between observations. The first thing we can apply are so-called proximity measures. That's something like correlation coefficients. For example, the Q coefficient, it's nothing else from a structure point of view as the Pearson correlation coefficient. And since correlation considers whether 2 data sets have a similar structure, if I use a proximity measure, so a difference measure built on something like these methods, I will get an idea which of the observations, considering the different characteristics I'm considering here, have a similar structure. High values in one area, low values in another area. That's the idea if I work with proximity measures. They are very good on detecting structures, on clustering according to structures. If I'm more interested in classical distances, which have values which are very close together, characteristics which are very close together, then I'm rather using something else. Then I'm using a distance measure. And well, there are quite a lot of distance measures. So just to give you a first short overview about those. Here we have the classical Euclidean distance. It's like if I have 2 points in space, the closest connection in a Euclidean space, so meaning in a flat space, would be the straight line from A to B. That's Euclidean distance. We can calculate this with the theorem of Pythagoras. And well, another alternative to this would be the squared Euclidean distance. That's a bit the idea that it punishes long distances more strongly and punishes small distances, a lot of small distance, less severely. That's one alternative. That's in some statistics programs even the standard approach. Alternatively, I could use something like the city block metric, which would then mean I consider not the direct line, but more or less the distance on one dimension and on the other dimensions, and always add this up. So this is like an absolute perspective on distances. It's like the three most common ones. Of course, again, I have quite a lot of other approaches there as well. Well, this already then also concludes this short session on clustering methods, because those are the aspects most important regarding deciding on which approach to use. Of course, later on we can also differentiate which fusion algorithms do we use, which approach do we use to decide what actually the distance is, depending on which measure we assume. Do we consider the next one, the on average next one? Do we apply different versions of merging two clusters? That's a question for fusion algorithms, but that's too specific to cover in this more general approach. So in this context, we're at the end of this short session. I say goodbye and see you next time.